There are principles and rules you must know when learning about electron configurations and orbital diagrams. They are the Aufbau principle, Hund's rule, and the Pauli exclusion principle. The physical and chemical properties of elements is determined by the atomic structure. The atomic structure is, in turn, determined by the electrons in which levels, sublevels, and orbitals they reside in. The rules placing electrons within the lowest levels is known as the Aufbau principle. The Aufbau principle states that each electron occupies the lowest energy level possible. Next is the Hund's rule. Hund's rule states that an electron with the same spin must occupy each orbital in a sublevel before electrons with the opposite spin are added to an orbital. This means that when writing an orbital diagram, all orbitals must have at least one of the same spins before putting an opposite spin in them. This is seen in the example right here, where sulfur, which has 16 electrons, is written out as an orbital diagram. It's 1s1, all these have it, but when you get to 3p6, when there is already 2, 4, 6, 8, 10, 12, 14 electrons there, so these two electrons wouldn't go in the same energy level, they'd be split between these two. And finally, there is the Pauli exclusion principle. The Pauli exclusion principle states that two electrons can be in the same orbital, but they must have opposite spins, which means one arrow up and one arrow down. Know about orbital diagrams is that they illustrate Hund's rule and the Pauli exclusion principle. You don't really see the Aufbau principle in this in orbital diagrams. Electron configuration notation lists the energy levels and sublevels, but not the orbitals. Okay. When you write an electron configuration, you will not see this. These arrows are not incorporated. Noble gas configurations can be used as a shortcut. We will go over this later on in the video. Here are the number of electrons located in each of the sublevels, S, P, D, and F. There are 2 in S, 6 in P, 10 in D, and 14 in F. All 4 of these sublevels are incorporated into the 4 energy levels. Here's a chart to easily help you understand energy levels. As you see, they're numbered 1, 2, 3, and 4. In the first energy level, there's only one sublevel. In the second, there's 2. In the third, there's 3. In the fourth, there's all 4. In the first, since there's only the S sublevel, there's two electrons in this energy level. And on the second energy level, since there's P, which has 6, plus 2, which is S, you get 8 electrons in that energy level. And energy level number 3, since we have S, 2, P, which has 6, and D, which has 10 electrons, you get a grand total of 18 for the third energy level. For the fourth energy level, there's the S sublevel, which has 2, P, which has 6, D, which has 10, and F, which has 14. If you add 14 plus 10 plus 6 plus 2, you get 32. So there are 32 electrons in the fourth energy level. Copy this down if you need. The sublevels are S, P, D, and F, and are located in each of the 4 energy levels. Below this, you see the Maid-Lung energy ordering rule, which is also called the Klitschkowski rule, mostly by French and Russian-speaking people. This can be used to write an electron configuration. As you see here, we will be attempting. We will also be writing a orbital diagram also. So first, we'll do this. As you see, the arrows point to which ones you use each of the times. So first, of course, is 1s. So write 1s. In 1s, there are 2 electrons. Or in an S sublevel, there are 2 electrons. So we'll do 2 arrows. Next, we go to 2s. So 2s, 2 electrons. Count up the arrows, 1, 2, 3, 4. Still 4 more electrons to go. So next, we will be doing 2p. The p sublevel has 6 electrons. So we'll have to do, and there's 4 left. So now we will be going back to our rules that we just learned, which include the Pauli exclusion principle and Hund's rule. So we'll put 1 here, 1 here, 1 here, That's 3. So then we put one more. And that's the electron configuration and orbital diagram for oxygen. Now we'll be learning about electron configurations. As you hear, there are 4 examples, and we're going to just do them all easily. So now, first we'll be starting with copper. 1s, and you put the number of electrons in the sublevel as an exponent. 2, 2s, 2, 2p, 6, 3s, 2. Let's count up how many electrons we have so far. We just count the exponents. 2 plus 6 is 8. 8 plus 2 is 10. 10 plus 2 is 12. So we have 12 out of 29. Still got to keep going. Next is 3p6. And then we go 4s2. Let's count how many we have so far. 2, 4, 10, 12, 18, 20. So we need 9 more. So as you know, the last one that we need is 3d. But what if we don't need 10 electrons? Well, then we just don't write it down. We write down however many we need, which is 9. So 3d9. So electron configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and finally 3d9. Next will be oxygen. Oxygen has 8 electrons, so we'll do 1s, 2, 2s, 2, and then since there's 4 already, it's 2p. How many more do we need? We need 4, so 2p, 4, and you're done. Next we'll be doing copper again, but whoa, has a -2 charge. Since it has a -2 charge, we'll be taking 29 and adding 2 electrons to it because it's a negative, which means it has more electrons. So 29 plus 2, that means there is 31 electrons. So that means we have to write an electron configuration with 31 electrons. Let's just copy that really quick. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 now because there's a whole 30. And then next is 5. No. And next is 4p1. Not 6, because we don't need 6 whole electrons, we only need 1. So that would be the electron configuration for copper -2. Next, we have oxygen plus 3. So we take the total number of electrons for oxygen, which is 8, and subtract 3 to that, because it's a positive charge, which means there's 3 more protons than electrons. So 8 minus 3 is 5, so we'll be running a electron configuration for only 5 electrons. So first comes 1s2, 2s2, that makes 4. So next you just do 2p to the first power, so 2, 4, 5. Easy way to check your answer, just count up your exponents. If they equal the number of electrons that you know you have, then you're done. Now you try. Write the electron configuration in orbital diagrams for iron. Go. Okay, here's the answer. So, if you look back at your Madelung ordering rules chart, you'll see that it goes first is 1s, this is the electron configuration, then 2s, then we have 4, 10, 12, 18, 20, And there's the D sublevel, which we only need 6, so we won't write down all 10. And there it is, the electron configuration. Now we will be doing the orbital diagram. There it is, the orbital diagram for iron. Now we will be learning how to do noble gas configurations. As you see here, this is how you would probably want to set up your periodic table that you have. Write down all the period numbers, 1 through 7, all the way down to francium. Write 1, 2, where the alkali earth metals, and the alkali metals are. That is S block. As you know, the energy level, the sublevel S, that's where you should recognize that from. The transition metals are the D block, which is 1 through 10, Scandinavium to zinc. Over here is the P block. That's from the boron family all the way to the noble gas. And that is P block, and you'll number that 1 through 6. Now, we're going to write our noble gas configurations for francium. Now what you want to do is go all the way to the right and then go up 1. That's how you find your noble gas. And you have to put that in brackets. Always put it in brackets. If you don't, it's wrong. Put it in brackets. So, as you see, we went all the way to the right, we went up, that's how we found our noble gas. So, the easiest way to find it, it's easy, okay? And then, now we'll go to the period number. 1, 2, 3, 4, 5, 6, 7. All the way down at the bottom, it's number 7. And it's an S block, so we put 7S. Now, we'll count the groups. 1. That's it. 7S1. That's your noble gas configuration. Now we're going to do something from D block. We're going to do mercury, which is Hg. Now instead of doing mercury's 80 electrons just to find the valence electrons, we'll just do the noble gas configuration and we'll get it easily. So now we go all the way to the right. So then we just go up 1. So the noble gas is xenon. Now, what we'll do is do the periods 1, 2, 3, 4, 5, 6. Period number 6. And as you can see, it goes completely out of the S block. So we'll write 6S2. Because it's obviously more than 2. Now, what we'll do is with the D block, what you have to do is you minus 1 energy level. So it'd be 5. I know that's confusing, but it's pretty easy. So you see the periods in, you take the first number, subtract 1 every time. And it's in the D block, so 5D. Now, what we're going to do is we're going to count all the way to mercury. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. it's in the 10th one. So 6s2, 5d10 is your noble gas configuration for mercury. Next, we're going to do boron. We go all the way to the right, up one. It's helium. Remember, brackets. Now, what we're going to do, as we know, periods. 1, 2. Second period. So, 2. It goes completely out of the S block. So, 2s2. And it does not come in contact with the D block, so we just forget about it for now. Now, it's in P, so you put 2P, and then we count 1, 2P, 1. There's the configuration for boron. Now, next, we're going to do thallium, which is Tl, right next to mercury. Brackets. Find it, go all the way to the right, up 1, see no. Now we count the periods. 1, 2, 3, 4, 5, 6. It's in the 6th period. Write down 6, goes completely out of the S block. S. Now this one, as you can see, cuts through D block. So we have to put in our noble gas configuration D block. So remember, you subtract 1, so it's 5 for the energy level, and it goes completely out of the D block, so 5D10. Now we go to the P block. It would be 6P, because you don't do anything with P, and 6P1. There's your noble gas configuration for thallium. Now, I want you to try on your own to do the noble gas configuration for selenium, Se, which has the atomic number of 34 on your periodic table. The noble gas configuration for selenium is argon as your noble gas, and then it's 4s2, 3d10, 4p4. This is the answer, of course, and that's what you got. Okay, now you try. Pause the video so you can complete the 4 of these. Now, tin has 50 electrons, so we'll just write the electron configuration for 50. 1s2, 2s2, 2p6, s10, 3s2, 3p6, 4s2, that's 2, 4, 10, 12, 18, 20. And we do 3d10, that's a total of 30. And then we do 4p6, it's 36. And then 5s2, which will get us 38. Then we'll do 4d10, which will get us 48. And then we're finally going to do 5p, and since we only need 2 more, 2, which will get us a total of 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, and finally 50. So next we'll bring nitrogen to the -2. Nitrogen originally has 7 electrons, so 7, we'll be adding 2, and we have 9 electrons. So we write down the electron configuration for 9. 1s2, 2s2, 2p5, ooh, almost caught me slipping. 2p5, which gets you 9. So it's 5 plus 4 is 9. So next we'll be doing sodium. Sodium has 11 electrons. We do 1s2, 2s2, 2p6, that gives you a total of 10, and then 3s1, because we only need one more electron to complete the 11. And that's your electron configuration for sodium. Next we have calcium, which has 20 electrons. Then we do 1s2, 2s2, 2p6, 3s2. How many is that? 2, 4, 10, 12. And then be 3p6. That'll get us 18. And then finally 4s2. If you count them up, 2, 8, 10, 16, 18, 20. Boom. Done.